Okay, my name is Bryce and I'm going to be talking about Conway's Game of Life with compute shaders implementation. So first off, how is the GPU used to accelerate the application? So I'm going to talk about the compute shader implementation at a high level. So firstly, in order to create a compute shader in Unity, you need a .compute file, which is going to be responsible for launching a kernel and running directly on the GPU. So within that file, we're using a pragma kernel compiler directive to indicate our kernel function, which is called game of life. Then when the kernel is launched, we call the function numThreads to determine how many threads will be available within each shader group during the execution of the function. And in addition to this, the kernel function is also responsible for determining the size of each pixel and its current location. And for the majority of our testing, we use numthreads 881, so we're launching a shader group with 64 threads. Thus, our kernel function, which is mostly responsible for tracking the number of neighbors for each pixel and determining the fate of the pixel based on the number of neighbors it has and whether it's alive or dead, is parallelized. So this way, our pixel calculations can run concurrently without having to iterate through the entire grid and make each pixel calculation sequentially. Okay, we have the code images. Here on the left, we have the code for the kernel function, which at a high level is responsible for calculating the number of neighbors for each pixel, and then determining whether to kill, leave alive, or revive each cell. And then on the right, we have the class, which is responsible for defining the input texture, and then controlling and sending the input texture to the kernel. Okay, so then I'm going to talk about the results when testing the compute shader version. So our results, we logged time taken in seconds to complete the game of life. However, in theory, the game should never really be completed, but since we're dealing with relatively basic rules and working with a relatively small grid, we often reach a point where the game will reiteratively kind of repeat the same pattern. So this is where we determined or decided to kind of consider the game to be finished and log the time at this point. So currently, a project shortcoming is that although the size of the grids are the same in the naive and the compute shader implementations, the naive implementation is using a random function to initialize the grid, as opposed to the compute shader version, which is converting images to an output texture to initialize the grid. So there's a difference in determinism between the naive and the compute shader implementation. However, we think that the results we found kind of make this negligible. Okay, so as you can see here on the right, we have the results in time. The red bar represents the compute shader version as opposed to the blue, which represents the naive implementation. And clearly we can see that the compute shader version performed much faster than the base game. Additionally, each run was performed with a different image and a different grid in the naive version to provide a little bit of diversity. We also chose images that had a both large and small amount of initial pixels. In addition to this, further speedup could have been achieved, most likely, by using the dispatch function, which could allow us to launch multiple shader groups. However, the default one was sufficient in testing. And that's all. Thank you. Okay, so moving on to the demo. First, I'm going to show our current naive implementation, which initializes a 512 by 512 grid. The background is going to be blue, and it's going to use a random function to initialize cells using a 16 by 16 black square image. So here we go. Okay, so at this point, it's going to continue the same pattern infinitely. Okay, so moving on to the compute shader version, it's going to look slightly different because it's taking an image as an input texture, converting it, and then running the game based on the output textures from that. So here we go. And there we go.